Okay, section 2.1, let's talk about instantaneous rate of change and tangent lines. But first, an example where we drop a tomato off the top of a 100-foot tall building, and we get some times that go along with its height as it falls down. So those are illustrated with the picture on the left-hand side, but also with the table on the right-hand side. So as you can see, we're at the top of the building at time 0, and the building is going to be 100 feet tall when we drop this tomato. Half a second later, we're 96 feet tall is where the tomato is, and so on with the rest of this table. So let's try to answer a few questions regarding this situation. So as you can see on question A, we want to know how long did it take for the tomato to drop 100 feet. We don't really need the n involved in there. All right, so to go the entire height from top of the building all the way to the bottom, that's going to be 2.5 seconds. Okay, as illustrated that we're at height 0 at the bottom of this chart, 2.5 seconds into the drop. All right, next, how far did the tomato fall during the first second? So the first second, that would have been, it started at time 0, and 1 second into its drop, it went from 100 feet all the way down to 84 feet. So that calculation would be 100 minus 84, or 16 feet. All right, on part C, how far did the tomato fall during the last second of its journey before it hit the ground? So the last second of its journey, just referring back to our chart, ended at 2.5 seconds in. Well, the last second, you back that up to 1.5 seconds in, it was 64 feet high, and it ended at 0 feet high, so that would have been 64 feet total during the last second. Part D, how far did the tomato fall between half a second and 1 second? Again, not too bad, we just have to be able to read the chart. Half a second in, it was a height of 96, and then 1 second in, it was a height of 84. So a quick subtraction here, 96 minus 84 should give us 12 feet during that time frame. All right, but now the questions get a little bit more difficult than just reading the chart. The next thing we'd like to know is what was the average velocity of the tomato during its fall? So that's going to be calculated by the total distance that it fell. That would be its position, as you can see with our formula at the top here, the change in position divided by the change in time. Okay, so the change in position was it fell 100 feet, and that took 2.5 seconds. All right, and the other thing that we want to be careful about here is that it was going to be moving a negative 100 feet throughout its journey. All right, the other way I like to think about this is average velocity or average rate of change can be thought of as the slope formula. Okay, so the slope formula most of us are comfortable with goes y2 minus y1 over x2 minus x1. I'm going to use m for slope or m for average rate of change. So if I want to visualize these as being ordered pairs, and sometimes getting the positive and negative is easier if you think of these as ordered pairs, we would say if you input 0 seconds into the journey, you're 100 feet tall, and it ends its journey 2.5 seconds in, it's going to be 0 feet tall. Let's treat these as our x1, y1, x2, y2. So I'd start with my y2, the 0, minus the y1, over x2, 2.5, minus x1, 0. Just so you can see, these are the 2's. These are the x sub 1, y sub 1. All right, doing that computation, we can now get our calculators out, help us out figuring out what is negative 100 divided by 2.5, and it works out to be negative 40, and our units here would be feet per second. So that would be the average velocity. Okay, what's the average velocity between times 1, t equals 1 second, and t equals 2 seconds? Well, on our table over on the side, we're going to look at 1 second and 2 seconds here. So treating those as ordered pairs, I'm going to go 1, 84 and 2, 36. So again, thinking average rate, average velocity, we're going to use x1, y1, x2, y2, and fill into our slope formula. So the average velocity is going to be 36 minus 84 over 2 minus 1. 36 minus 84 is going to be negative 48 over 1, and this will be in feet per second. We could simplify down and just say that's negative 48 feet per second. All right, one last question to go along with this. How fast was the tomato falling 1 second after it was dropped? All right, now this is a more difficult question because we don't know exactly what the speed was on this tomato. We have to make an estimation here, and to do so, what we've done is, over on the right-hand side, you can see this graph. What that graph is it's the same values that are up in our table, simply plotted on an axis. So zooming in here, you can see that what we have is 1 second into our journey would correspond with this point, this ordered pair on here. The other thing that we've also computed is between half a second in and 1 second in, we calculated that the slope of this line was negative 24 feet per second. Remember, the slope is equivalent to the average velocity, or average rate of change. The other one that we have computed here is between 1 and 1.5 seconds in. That was actually the first computation that we did, which was negative 40 feet per second. All right, what we're actually trying to do here is we are looking to figure out what is the slope of this tangent line, a line that only intersects the graph in that one specific point at 1, and basically barely touches the graph. All right, that's what we refer to as a tangent line. And mine may be illustrated, maybe it needs to be just a little bit further this way. Nope, can't move it. All right, you get the idea though that if we take a look at our graph, that black line is only touching this one point. It's not really touching any other points on the graph. So far we've actually calculated the blue line here as a secant line because it hits 2 points on the graph. The dash line hits these 2 points on the graph. So it also is a secant line, verbiage, secant. But we're looking for a tangent line, or the slope of that tangent line, the black one. Well, we can get a pretty good estimation for what that is because it looks like it's in between the blue and the black dash lines. Well, those were negative 24 feet per second and 40 feet per second. Or sorry, negative 40 feet per second. So what I'm going to do is go ahead and take the average of those two. That'll get us a value somewhere in between the two. So to take the average, I've added the two together, and I'm going to divide by 2. I believe these add up to negative 64 divided by 2. It's going to be right around negative 32, and that would be in feet per second to get an approximation for the exact velocity that this tomato was traveling 1 second into its journey. It's got to be somewhere in between negative 40 and negative 24. All right, hope this helps out as we're trying to get down what secant lines are, average velocities, and tangent lines.